welcome back. So I had a look, since I knew that the deadline to withdraw from courses was coming up. I had to look at the grades and I realized that a lot of your grades aren't entered. Like a couple entries in the grade book aren't in. So I will take care of that by this afternoon. Um, so by this afternoon, you should have a either entirely complete or almost entirely complete grade book. And I don't anticipate it changing people's minds one way or the other. Everyone's grades are pretty good. Which also leads me to I had gotten a couple of emails about exam two, and I had mentioned that I was gonna decide what to do about exam two. So when I wrote exam one, I the first draft of exam one was a little bit more involved, and I felt like wasn't really kind of sort of in keeping with the spirit of the course, and so I ultimately abandoned it and rewrote it. And so the version of exam one you got was very similar to homework. It was kind of like glorified homework, but I thought that it didn't make a whole lot of sense to like pick out, even though it tried to be a survey of the stuff that was done. It definitely focused more on like a particular part of the course. It didn't really feel like it made much sense to like elevate those questions above your normal homework questions. And so I'm going to uh, slightly rescale the weighting in the syllabus, but ultimately what I'm doing is kind of a Sisyphean task because it's not going to make a difference really. I'm kind of just doing it uh, out of principle. It's not going to change anyone's grade, I don't think, because like I said, I think everyone did well. But all those grades will be entered by this afternoon. I'll make sure of that, and then that way at least by tonight you'll know. Even if, like I said, it's not gonna cause anyone to make any different decision they would otherwise make. Anyway, okay, so that out of the way, I'll send out an announcement when I do that. You're gonna have two more homeworks. So one I will post later today, and the other I'll post next Monday. It'll be due on the last day of class. And after that, we have the final exam, which I'm going to structure a bit differently. It's your final is going to be like half kind of homework and half, we'll say, almost like a report. So less, like I said, half of it will kind of be like the homework, and half will be you writing a bit. It's not going to be a serious like writing assignment, but just writing a bit about some topic that you can pick. So I'll present a list of topics, and you can pick one of them that you're most interested in, and write a little blurb about it. So anyway, I'll let you know as that gets a little closer how that's going to go. Okay, so with that said, at the end of class last time, we were finishing up, or I guess I was basically starting with reminder of our definition of the quaternions. So we represented quaternions by these 2x2 matrices with complex entries of this form. Of course, the more familiar way that you'd seen this earlier in the course was written out as this quadruple ABCD with these vectors 1, I, j, and k, satisfying these algebraic relations here. And so this, defining the quaternions like this, we saw that this map scaled distances in a way that was predictable. So it scaled them by the length of this quadruple Q, which we saw, if we considered this as a point in R4, this is actually just the distance from this point to the origin. Okay, and this could be expressed in terms of the determinant of Q as a matrix, which was literally this distance, a squared plus b squared plus c squared plus d squared. Right, sorry, it's the distance squared. So anyway, this was our build-up for ultimately what we were interested in was that, of course, since we know that this multiplication scales by this length of Q, then that same multiplication is an isometry if the length of Q is 1, right? It's an isometry by definition of, isometry preserving distance, right? So this multiplication preserves distance in R4 if the length of Q is 1. Okay. And as I mentioned last time, and of course, since multiplication of the quaternions is not commutative, we have to have a separate statement saying multiplication on both the right and the left satisfy this property, because those are typically different products, right? Those are different maps, typically, because the quaternions are not commutative. Okay, and so anyway, it turns out that these are extremely useful for studying rotations of R3. So to see why that is, and you might have guessed this already when we were earlier talking about quaternions, using them as our base space for defining the quaternion projective plane. Right, when we were talking about them, then one of the things you might have noticed about these algebraic relations, just bringing them back again. So these algebraic relations, the IJKs you see here definitely remind you, or should remind you maybe, of the IJKs you encountered when expressing a vector in that IJK notation, right, from like Calc 3. Okay. Cooper, no. So the final will not be the 2-day to do format. You will be given more time. So I have to look again, but I can't remember off the top of my head exactly when our final is scheduled. If it were in person, it will be due then, and I will assign it roughly a week before, since there's this little extra component. I'm not, like I said, don't be too scared by the writing / almost like book report form of part of the exam. It's not going to be a big deal. So anyway, that's I was just giving you a heads up on that. So you'll have like 5 days to a week to do it is when I will post your final. And so, like I said, it will be due at 11:59 on whatever day our final is scheduled. I could find that out in a couple seconds, but I'm going to continue on with the lecture. But I'll post that when I make the announcement. Okay. So the IJK, you might might have already noticed that the IJ and K, remind you of the IJ and K that you encountered in Calc 3. Okay, and so to see this, we consider looking at rotations of IJK space. Or what is IJK space? So IJK space is the subspace of the quaternions, right? So it's a subset of quaternions that look like a particular form or have a particular form. So if P is any quaternion in IJK space, so what does it look like? Then P looks like a triple xi plus yj plus zk. Where have you seen that before, right? Where x, y, and z are real numbers. Now, it doesn't take a lot of imagination to think about that for a second. Say, this definitely seems like it's the same space as R3, so long as these ij and k's behave in the proper way. But if you go back to those relations for the quaternions, those essentially guarantee that that's exactly what happens here. Okay, and if Q is a non-zero quaternion, not necessarily an IJK space, just a non-zero quaternion. So if Q is a non-zero quaternion, then the map, or maybe I'll start out by saying that Q, P, Q inverse, so this is called conjugating the element P. But Q, P, Q inverse is also an IJK space. And so what this is saying is that if you take a quaternion that's already in IJK space and you form this conjugate QP inverse for any non-zero quaternion Q, so Q might not be in IJK space, but if you form this this conjugate element involving P that is in IJK space, then you get something that is still in IJK space. And so this thing preserves a quaternion being in IJK space. Okay, that's not affected by doing this operation. Okay. All right. And so thus, if the length of Q is 1, then not only is this previous statement still true. So this previous statement is true regardless of what the length of Q is. Q just needs to be a non-zero quaternion. But if the length of Q is 1, then the map that sends P to QPQ inverse is actually an isometry. From that aforementioned fact that doing this multiplication by quaternions on both sides, right? So we had this statement that both of these maps were isometry if the length of Q is 1. So this is kind of like a combination where you're multiplying by Q on the left and Q inverse on the right. And so this Q inverse for quaternions will you will investigate that in your next homework. So your next homework is going to involve the quaternions almost entirely. That's what you're going to be asked to do computations for. Anyway, so QP inverse is also an IJK space. So if the length of Q is 1, then the map that sends P to QPQ inverse is an isometry of R3. Where did R3 come from? Well, note that IJK space is just the set of triples XYZ. Right. I.e., IJK space is a copy of R3. Right? It is isomorphic to R3. Okay, as a space. Okay. Now, to help us see what it is that we're doing with this, right? So this is the map that's going to get it done for us. Okay, so let me box this. I'll rewrite the statement here in a second. So this is the map that's going to get done for us. But to see how this is going to, or how this relates to rotations of R3, also, any non-zero quaternion with length 1 can be written in the form Q is cosine of theta over 2 plus L I plus MJ plus NK times sine of theta over 2. Okay, where L, M, and N are real numbers such that L squared plus M squared plus N squared is equal to 1. Okay. All right. So you may see where this is going. So any quaternion with length 1 can be written in this form. And so let's say that Q is written in that form. This isometry can be seen readily to be a rotation, and we'll show that fact. Okay, so supposing Q is in that form, then the map that sends P to Q, P, Q inverse is an isometry of R3, which turns out to be the rotation through angle theta. It's the rotation through angle theta about the axis through 0, the origin, and the point L I plus mj plus nk. Okay. And so this map that takes a point in ijk space and conjugates it by some non-zero quaternion q, this is rotation through an angle theta about that axis specified there, and this is the theta, and the L, M, and N are referring to this non-zero quaternion q being written in this form. Okay. Now, your first question might be, wait, so why is the angle showing up here is theta over 2, right? But this is rotation through an angle theta, so why the difference? Because this, when you take P, what you're doing to it is you're multiplying it by both Q and Q inverse. And Q inverse is going to contain terms that also have theta over 2, cosine theta over 2 and sine theta over 2 in them. And so multiplying by Q is the theta over 2 part. That's how much of the rotation you get. And multiplying by Q inverse is the other theta over 2 part. So combined, it's rotation through an angle theta. That's essentially what's going on here. Okay. All right. And so this gives us by far the most convenient way of talking about rotations of R3. So this gives us a very convenient way of describing rotations of R3. So viewing non-zero quaternions as being associated to rotations of R3 is just really, really, really nice. It might not seem like it at first. It might seem like quaternions are kind of this nasty, exotic thing, and it seems like a lot of trouble to describe rotations of R3. But honestly, when you try to describe rotations of R3, otherwise it's nastier, I think. So this is not nearly as bad as it seems. Actually, it's really, really, really nice. And so let's see what's going on here. So what's happening? So what is going on here? Now, we could kind of directly do this computation if we really wanted to. But if we restrict ourselves to some special cases, we can basically get it done to see what's happening. So some of the computations, if you're going to do this directly, might be a little bit tedious, but we can be a little bit smarter about it and just restrict our attention to some special cases. So let's look at some special cases. So let's look at the special case where the axis of rotation is in the I direction. And in this case, we'll see what happens. So we'll see exactly what happens. All right, so we pick the axis of rotation in the I direction. Then this rotation in question through an angle theta is going to take a particularly easy form. It's just going to be, instead of having, let me bring back up my form for Q again. So instead of Q being in this more general form, I can just choose this L to be 1 and M and N to be 0. So this would just be cosine theta over 2 plus I sine theta over 2. Okay, and so the example that we'll look at is P is my point in IJK space, or R3, and I'm looking at the map P, Q, P inverse, or Q inverse, sorry, where Q is this quaternion. It's cosine theta over 2 plus I sine theta over 2. Okay. Now, it being in the special form allows us to easily compute Q inverse. Actually, thinking about the inverse of a quaternion, right? Well, remember, we expressed quaternions as complex matrices. Okay, complex 2 by 2 matrices. So the question is, an inverse for that Q should correspond to the inverse of that matrix. How do you find the inverse of a complex matrix? Well, like I said, I'm going to leave that to your homework. But for this, well, this type of Q is just going to behave like a complex number, right? And so finding what is Q inverse here is really easy, right? I conjugate and divide by the length, but the length of this thing is going to be 1, so it's just me doing complex conjugation. Sorry, I said conjugate there, should have been specific. So I would treat this as complex number and complex conjugate this thing, and that's all I have to do because it has length 1 to find my Q inverse. So that's nice. So what's the first thing we want to check? So check any point on the x-axis, or sorry, I should say the I-axis. So any point on the I-axis is fixed. Okay, so what is a point on the I-axis, right? So a point on the I-axis looks like just some generic x times the vector I. Okay, and so what we want to look at is Q xi Q inverse. Do we have enough room? We have enough room to do it here, I think. So, okay, so Q xi Q inverse. What does this look like if I write this out? So Q is cosine of theta over 2 plus I sine of theta over 2 times x, which is just a real number, times vector I, times what is Q inverse? As I said, we're treating this, because of the rules, the algebraic rules for the quaternions, this behaves just like a complex number. So finding Q inverse, I would conjugate divide by the length, but the length of this is going to be 1. And so all I have to do is complex conjugate this thing. So this is cosine of theta over 2 minus I sine of theta over 2. I don't know why I wrote parentheses for that one. All right, maybe I'm not going to have enough room. Okay, so what do I get now if I distribute all this stuff? So first we can distribute the xi here, if you like. So distributing xi, this is cosine theta over 2 plus I sine theta over 2 times xi cosine theta over 2 minus, so this is going to be minus xi, but I times I is what? What is I squared? Well, I squared, if we go back to our rules for the quaternions real quick, I squared is, oh, that is incorrect. What happened there? I squared is minus 1 here. Okay, it's this minus 1 vector, right, if we're writing a quaternion like this. So yeah, I squared is minus 1 here. Okay, and so this is so it's not quite the same as the complex numbers, but the behavior is essentially the same here, right? That's the point. So this is x I times minus I, so this is plus x times this vector 1 right, times sine of theta over 2. Okay. And now if I distribute this thing and group the terms here, so I'm going to have xi times cosine theta over 2 times cosine theta over 2. So I'm going to have xi cosine squared theta over 2. And I'm also going to have xi, so here I'm going to have x times, well, let's just write out all these mixed terms. So where's my other xi term coming in? So here I would have x times 1 sine theta over 2 times I sine theta over 2. So that would be another xi sine squared theta over 2. And so I can factor out an xi from cosine squared, or what is inside the parentheses, cosine squared theta over 2 plus sine squared theta over 2. Okay. I had to do that part in my head to save myself room on this sheet. Maybe I should have just went to the next sheet. Plus, if I factor one vector out of what's remaining, I have the mixed terms. The mixed terms become what? So I have one vector times, so here I have, so this is going to be sine theta over 2 times minus, so multiplied by cosine. So this would be sine theta over 2 cosine theta over 2. So that's plus sine theta over 2 cosine theta over 2. And then the other mixed term, because of this, so this would be an x here. It'd be an x in both those terms. So or x would be in one of those terms, but this would be a minus sine theta over 2 cosine theta over 2. Okay, and so this term is 0, and this is 1, and so what is left is xi. So indeed, this works out. Okay, so it took xi to xi, which it should have, because this should be a rotation of angle theta in the the axis that's in the I direction. So you can take the axis to just be the I axis. So it should fix points on the I axis, which it does, and then we have to check that it rotates the other points in the way that it does. So now we check the next thing, which is we check that the point represented by this j vector is rotated through angle theta to the point. So this is through angle theta in the jk plane. To the point j cosine theta plus k sine theta. All right. And so you can think about what a generic point on the j axis should be rotated to, but we can just pick j. The reason we're picking j is ultimately we want to use the fact that this can be determined by where it sends 3 points that are not collinear, right? So we have this fact about R3, and so what this isometry does should be determined by what it does to 3 non-collinear points. Okay, so we're picking this specific point just to make things easy. All right, so now I want to check what j gets sent to. So if I look at q, j, q inverse, what is this rewriting? So this is cosine theta over 2 plus I sine theta over 2. And this is times j times cosine theta over 2 minus I sine theta over 2. Okay. All right. And so what happens here? Well, if I distribute j through in this second term, what do I get? I have cosine theta over 2 plus I sine theta over 2. Distributing j, I would have j cosine of theta over 2. And then I'd have j times I, but there's a minus sign out front. And so going back to our quaternion rules, what is minus j times I? That's k. Right, so minus j times I is k, and I have to pay attention to the order that this happens in. So minus ji, which is what I have here, becomes k. So this is plus k sine theta over 2. Okay. Now looking at this, you might already make the argument for what exactly is happening here. So I almost have the point that I want. I want j cosine theta plus k sine theta. I have j cosine theta over 2 plus k sine theta over 2. I'm literally halfway rotated there. What does multiplication on the left by this quantity do? It rotates me the remaining theta over 2 bits. So I'm actually done here, but to see algebraically why this works, right? So intuitively from this step, if you understand what's going on there, that multiplying on the left by this thing is going to rotate this point, the other theta over 2 about the y-axis, and it's going to get you exactly to the point that we want. But let's actually multiply this out. So if I multiply this out after expanding this, I can factor j out of quantity cosine squared theta over 2 minus sine squared theta over 2. Okay, plus k times 2 sine theta over 2 cosine theta over 2. Okay. And I can do that after going through a few facts here, right? So this, going from this step to this step is since minus ji is equal to k. Getting from here to here, I need to, when I'm doing this combination, I have to keep track of what each of these multiplications are, right? And I have to pay attention to what order I do them in, right? Because that matters. And so when I write this out, what do I get? Why do I get this? This is because ik is equal to j, and ij is equal to k. All right, so keeping track of those. Ij is k, so that's where that factor of k comes from. Ik is j, and so that's where that extra factor of j comes from. So that's why this factors in this way. Okay, but of course, all right, simplifying this, what I get is j cosine theta plus k sine theta, and I'm done. That's exactly the point that I wanted. So it was rotated in exactly the right way. Now, we could check that the point k gets rotated in the way that it should. So similarly, I mean, it's identical to this computation, basically just using the other corresponding identities here. So similarly, we can check that this map takes the point k and sends it to minus k sine theta plus j cosine theta. If you think for a second, you'll see that that is the point that it needs to get rotated to. Thus, after seeing what it does to 3 points, we can pick any point that we want on the y-axis because it gets fixed. And so similarly, we can check these. I mean, we've already checked this one. We can check this other thing, and thus the isometry that takes a point in R3 and sends it to QP, Q inverse, is a rotation of the JK plane rotation of the JK plane through theta because it agrees with that rotation on the 3 points listed. And this is sufficient since our 3 points are not collinear. So the reason for this being that we have our 3-point determination for isometries, right? So don't get confused by what we did in the projective geometry chapters. We have 3-point determination for isometries of R3. And so any isometry of a plane is determined by what it does to 3 points not in a line, right? So recall any isometry of a plane. You might say, wait, this is an isometry of space. Yeah, but the rotation we're doing is in the JK plane, right? So any isometry of a plane is determined by what it does to 3 non-collinear points. That are not collinear in that plane. Okay, we did this in, this is in chapter 3. This is what we did near the end of chapter 3. Okay. Okay. So thus, the isometry that sends P to QPQ inverse is, or I should say it leaves the I-axis fixed and rotates the JK plane through angle theta. So it's a rotation through angle theta about the I-axis. Okay. Now that was for our particular example. It is tedious, but not really fundamentally more difficult to actually just compute, like directly compute that, oh, in fact, like I can describe any space rotation in this way. So if you write out, all right, if you write out in a general form of a space rotation, you can show that there exists a quaternion Q that gets this done. Okay, in fact, we'll see here in a second that not just one quaternion, but there's actually a pair of quaternions that does it, namely that quaternion and minus that quaternion work. And so, note, if Q is a rotation of R3. What do we mean by that? We mean, I'm saying Q is a rotation of R3. Really, it represents some rotation of R3. If Q is a rotation of R3, then minus Q is the same rotation. That might seem weird. Why? Well, QP, Q inverse, is the same as minus Q, P minus Q inverse. Right. Okay, thus, rotations of R3 actually correspond to pairs of quaternions. So we'll see. This is more important for some of the finite geometry applications that I'm going to skip over for now. I may have time to return to them before the end of the semester, but to really cover all of the non-Euclidean geometry stuff in the very last chapter, I have to, unfortunately, skip over them for now to make sure that we get to that stuff. So this is, this might not seem like that important of a distinction, but we'll actually see here in a second another way in which this kind of similar idea comes up. And so that is what I wanted to say about representing space rotations by quaternions. But I wanted to say one more thing. So what we are skipping for now is the contents of 7.7. So this is a finite group of space rotations. This is very interesting stuff. But to fully talk about it would probably take me a lecture and a half, maybe a little bit more. And unfortunately, like I said, I really, really want to get to the stuff that's kind of more important for the overall view of the course. And so in order to do that, I'm going to skip this for now. Might be able to get back to it in a little bit, but skipping it for now. And so one more thing I wanted to say in this chapter. So one more thing. I want to say something about the groups S3 and RP3. Okay, we've defined both of these things before, but we didn't define them as mathematical groups. We defined them as spaces we were interested in. Right? And so S3 is the 3-sphere. RP3 is real projective space. Right? Three-dimensional real projective space. So this is the 3-sphere. Okay, that is not the sphere that sits inside three-dimensional space. That's the 2-sphere, right? Because the sphere that you're used to that sits inside two-dimensional space is only 2 dimensions, right? You only need 2 parameters to describe where you are, right? Latitude and longitude. The 3-sphere is the 3-dimensional sphere, so it is the same object as S2 is in R3, sitting inside R4. All right, so S3 sits inside. Maybe I should say it like that rather than saying it's the same object in some analogy. I should say that S3 sits inside R4 just like S2 sits inside R3. Okay, and so this is the 3-sphere, and this is real projective space. Okay, that we defined in similar analogy to the same way we defined RP1 and RP2. So right, so this is 3-dimensional real projective space. Okay, and so the idea here is to see how these things are related to quaternions and rotations. Okay, and so the idea is, so S3 is just defined as we did before. It's defined as the set of quadruples A, B, C, D, right, in R4, such that they have distance 1 to the origin in R4. Right. Okay. But now you see that this actually corresponds to points that are just quaternions, right? Thus, a point ABCD on S3 corresponds to quaternions that look like A1 plus BI plus CJ plus DK. Okay, with length 1. All right, they don't correspond to just any old quaternion, but they correspond to the quaternions of length 1. Okay. what does this tell me? Well, what we just said is that a quaternion is a rotation of R3, right? And so I can think about S2 sitting inside R3. So if a quaternion is a rotation of R3, it is also a rotation of the sphere S2 sitting inside R3, but a point on S3 corresponds to a quaternion, and so points on S3, the 3 sphere, correspond in this way, if we trace through it, to rotations of S2. Huh. So then, what am I saying here? Let's rewrite all of this now that I've said this vector. Thus, rotations of S2, which correspond, since S2 sits inside R3, and a rotation of S2 is going to be a rotation of S3 or of R3, which corresponds to a quaternion or a pair of quaternions. So thus rotations of S2, which correspond to pairs plus minus q of quaternions, correspond to point pairs plus minus ABCD of S3. These are antipodal points. Huh. Geometrically, this might seem a little weird at first because this correspondence goes through the quaternions, but rotations of the 2 sphere correspond to antipodal point pairs of the 3 sphere. How does that work? Well, a nice way of actually thinking about this is the following, and it involves RP3, right? So recall, how is RP3 defined, right? So what are the points in RP3? So points are lines through the origin in R4, right? But a line through O in R4 meets S3 in antipodal point pairs. Plus minus A, B, C, D. So you may not be able to actually draw S3 sensibly because it has to sit inside 4 space. But what's nice is if I just think, right, like if I use my brain and try to imagine this, I have this 3-dimensional sphere. It behaves just like a higher dimensional analog of S2, my 2 sphere. And so I know how lines through the origin in R3 intersect S2, right? Pick any line you want to. Through the origin in R3, it's going to intersect the sphere centered at the origin in R3 in antipodal point pairs, right? It's going to intersect at antipodal points. It's only going to hit them at 2 points. They're going to be antipodal points for the sphere. So the same thing is going to be true if I just crank up the dimension by 1. So now lines to the origin in R4 are going to intersect S3 in antipodal point pairs. Okay. Thus, point pairs plus minus A, B, C, D also correspond to points of RP3. So that's all I'm going to say now because I ran out of time, but I will spend like 2 minutes saying one or two more sentences on Wednesday, and then we will begin our last chapter, the very last thing that we're going to talk about in this course. So anyway, keep an eye out. I know I've been saying that, but now is going to be a real dump of info, but not work, so you don't have to panic too much. Anyway, so I will be sending out some announcements later today, later in the afternoon. So I will see you all on Wednesday.